Hello everyone. In this video we'll be looking at another set of substitution techniques. The focus of today will be on trigonometry. We'll add a couple new trig identities to our repertoire to start, and then try a few integrals involving trig functions. These might seem a little daunting at first, but you'll get the hang of it eventually with the more problems you do. The good news is there's generally a limited number of things we can try with each question, and as always, if you try something that doesn't work, just try again. You can't expect to grow and improve if you stay within your comfort zone. So hopefully you recognize these trig identities. These are all on our formula sheet. And we're going to add a couple more here that we're going to prove right now. We'll start by proving this one. The right hand side is 1/2 1 minus cos 2 theta. We're going to use this identity. So we're going to sub in cos squared x minus sine squared x. So the right hand side of this equation will become 1/2 1 minus cos squared x, or theta, minus sine squared theta. And we can rewrite the stuff in the brackets, so that would be 1/2 1 minus cos squared theta plus sine squared theta. And knowing that cos squared theta plus sine squared theta is equal to 1, we can substitute 1 minus cos squared theta. We know that's equal to sine squared theta. So within the brackets here we have sine squared theta plus sine squared theta, which is 2 sine squared theta. And if we multiply that by 1/2, we get sine squared theta, which is equal to the left-hand side. And the proof for this identity is basically the same, except that subtraction symbol is an addition symbol. So you can pause the video if you want to have a look through that. So for this first set of problems, we need to use trig identities to determine each of the following indefinite integrals. This first one doesn't even look like we need to use trig identities. We can use our substitution techniques developed from last class. So if we let u be cos of theta, then du is equal to negative sine theta d theta. And I can see a sine theta d theta appear here. So that means negative du is equal to sine theta d theta. So then this original integral will become u to the 5th du. Did I miss anything? There should be a negative sign here. So u to the 5th would have come from a u to the 6th divided by 6 plus c. And we can sub cos theta back in for u now. So we would have negative 1/6 cos theta to the 6th plus c. Now for the next one. So here we have sine cubed cos squared. We could maybe try expressing that as 1 minus sine squared. Let's see where that takes us. So sine cubed theta, 1 minus sine squared theta, d theta. And I guess we could distribute this sine cubed in. So that would give us sine cubed d theta minus sine to the 5th d theta. And I guess we could try subbing in a sine theta. So then du would be cos theta d theta. Now unfortunately I don't have a cos theta d theta in either of these integrals, so it looks like we should probably try something else. Now we don't have a sine cubed identity, but we have an identity for sine squared. So why don't we split up the sine cubed into sine squared theta, sine theta. And we have cos squared theta d theta as well. So now we could try expressing sine squared theta as 1 minus cos squared theta. So we have 1 minus cos squared theta, sine theta, cos theta d theta. And if we let u be cos theta, then du is equal to negative sine theta d theta, which looks promising because I have a sine theta d theta here. So sine theta d theta will be negative du, and our integral will become negative 1 minus u squared du. And we can distribute the u squared into the brackets, so we will have u squared minus u to the 4 du. And u squared would have come from a u cubed divided by 3, and u to the 4 would have come from a u to the 5 divided by 5. And we should also add a constant. And now at this point we can sub cos theta back in for u. So we'll have negative 1/3 cos cubed theta plus 1/5 cos 5th theta plus c. So let's try a few more. So sine squared theta, we could try 1 minus cos squared theta, d theta. But the obvious choice here for substituting would be cos theta, and du being negative sine theta d theta is a bit of a problem because we don't see any sine theta d theta in this integral. So it looks like we should try something else. We might have some luck using the identity that we introduced earlier. So let's try substituting sine squared theta, and we'll use 1/2 1 minus cos 2 theta. And we can split this integral up, so we would have 1/2 d theta minus 1/2 cos 2 theta d theta. So this first one's fairly easy. It would be 1/2 theta, and with this one you might like to substitute a 2 theta. So then du would be 2 d theta. So it looks like d theta would be du over 2, and we'd eventually get negative 1/4 sine of u, and u is 2 theta. And don't forget to add a constant. So this would be fine enough as a final answer, but we could also use the identity sine 2 theta equals 2 sine theta cos theta, and sub in for that, and we would get 1/2 theta minus sine theta cos theta. Either one is fine. On to the next one. So we've got sine squared cos squared, and we'll try something. Again, it might not work, but we'll see. So we'll go 1/2 1 minus cos 2 theta, and 1/2 1 plus cos 2 theta. So I can bring these two 1/2s out front. So I would have 1/4, and 1 minus cos 2 theta times 1 plus cos 2 theta is a difference of squares. So that would eventually give us 1 minus cos squared of 2 theta. And we can use the identity cos squared theta plus sine squared theta equals 1. So therefore 1 minus cos squared of 2 theta would equal just sine squared of 2 theta. So we would have 1/4 sine squared 2 theta d theta. And from here we can use the identity again. So we could do 1/2 1 minus cos 4 theta, which would be fine, and we'd basically do the same thing that we did above. But we could also make the substitution for 2 theta, so we could do u equals 2 theta, so then du equals 2 d theta, so then d theta equals du over 2, so I can replace that with a du over 2, and 2 theta with a u, so this would work out to 1/8 sine squared u du. You may notice we did this one a moment ago, so we don't have to do it again. So next we would have 1/8 1/2 u minus 1/4 sine 2u. And we can factor out a 1/4 from each of these terms. So we would have 1 over 32, 2u minus sine 2u. Forgot the c. Should be a c there. And now we can sub 2 theta back in for u. So we'd have finally 1 over 32, 4 theta minus sine 4 theta plus c. So now we'll try a definite integral. So here we have a cos cubed sine to the 4th. We'll maybe start by trying to split this up into cos squared theta, cos theta. And the reason I do that is because there are a couple identities we can try for cos squared theta. So we might try 1/2 1 plus cos 2 theta times cos theta. But the issue with that choice is now we have a double angle and a couple single angles. So it might be better to try replacing cos squared theta with a 1 minus sine squared theta. And then our integral would become 0 to pi over 2, 1 minus sine squared theta, cos theta, sine to the 4th. And the obvious choice for a regular substitution here would probably be sine theta. So u equals sine theta. That means du is equal to cos theta d theta. And that's great because we have a cos theta d theta in the integral. And now we just need to figure out what our new limits of integration will be. So when theta equals 0, u equals sine of 0, so sine at 0 is 0. And when theta equals pi over 2, sine at pi over 2 is 1. So now we can rewrite this integral from 0 to 1. We would have 1 minus u squared, and cos theta d theta is equal to du, and then sine to the 4th theta would be u to the 4th. So now we can distribute this u to the 4th into each of these terms, and that would give us from 0 to 1, u to the 4th minus u to the 6th du, and u to the 4th would have come from a u to the 5th divided by 5, and u to the 6th would have come from u to the 7th divided by 7, and we're doing that from 0 to 1. So next we would have 1 to the 5th divided by 5 minus 1 to the 7th divided by 7 minus 0 to the 5th divided by 5 minus 0 to the 7th divided by 7, so that's basically just 0. So we would do 1/5 minus 1/7, which is 2 over 35. So this next one I'll let you do. I'll leave it to you to prove that this is the result. A good opening move with this integral would be to express this as cos squared theta times cos theta. Now expressing cos squared theta with this identity probably wouldn't be a great choice because we'd have a double angle and a single angle. So it might be better to make use of this identity here. So don't do that one, I wouldn't recommend it. Maybe do that one. The actual integral is fairly easy. The fraction and radical work getting to the final form is a bit more work, but it's also fairly reasonable. So on to the last question of the day. Use integrals to determine the area between cos squared theta and sine squared theta for this interval, negative pi over 8 to pi over 8. So remember from last unit, if we have two functions f and g, and we have f above g on an interval, we can make a new function given by this equation, and the area is given by this. So that's basically what we're going to do right now. So because we know cos squared is above sine squared on the interval from negative pi over 8 to pi over 8, we can say the following about this area. It's the integral from negative pi over 8 to pi over 8, and we do cos squared theta minus sine squared theta. So from here we could maybe try using our new identities. So we'll let cos squared theta be 1/2 1 plus cos 2 theta, and sine squared theta be 1/2 1 minus cos 2 theta. So next we can maybe pull out a factor of 1/2. So we would have 1/2, and then we might be able to simplify this a little bit. So we have 1 plus cos 2 theta minus 1 plus cos 2 theta d theta, and 1 minus 1 is 0, and we have 2 cos 2 theta. So next we'll have 1/2 2 cos 2 theta d theta, which would simplify further. We can pull the 2 out, so now we'll have negative pi over 8 to pi over 8 cos 2 theta d theta. And if you like at this point you can substitute a 2 theta, but cos 2 theta would have come from 1/2 sine 2 theta. So this would be 1/2 sine 2 theta from negative pi over 8 to pi over 8. And now we just sub in pi over 8. So we would have 1/2 sine at pi over 4 minus sine at negative pi over 4. And next we have sine at pi over 4. So sine at pi over 4 is 1 over root 2. And sine at negative pi over 4 is negative 1 over root 2. So in the brackets here we basically have 2 over root 2. And if we multiply that by 1/2, we just get 1 over root 2. So that's it for me for today. There's a nice little summary on page 516 and 517 for each of these scenarios we went over today. You can try some of the textbook questions out as well, and I'll see you next time.